Welcome to Tech Lab by Sid. What is recursion? Recursion is a programming technique in which a function calls itself in order to solve a problem. It's a way of breaking down a problem into smaller, more manageable subproblems that are similar to the original one. The key to recursion is the base case, or stopping condition, which ensures that the function eventually stops calling itself. Key concepts of recursion. Recursive case. This is the part where the function calls itself with modified arguments, gradually reducing the problem size. Base case. The condition under which the recursion ends. Without a base case, the function would call itself indefinitely, leading to a stack overflow error. Common use cases. Factorial calculation. Fibonacci sequence. Tree and graph traversal example depth first search. Divide and conquer algorithms example merge sort, quick sort. Backtracking problems example n-queens, Sudoku solver. Pros of recursion. Recursion is often simpler and more elegant for problems that have a repetitive structure, example, tree traversal, backtracking problems, or mathematical problems like factorials or Fibonacci numbers. It can make code easier to write and understand for some problems. Cons of recursion. Recursion can be less efficient in terms of memory usage due to the call stack. Every recursive call adds a new frame to the stack, which can lead to a stack overflow if the recursion depth is too deep. In some cases, recursion can be slower than iterative solutions due to overhead from function calls. Terms related to recursion. Recursive function. A function that calls itself in order to solve smaller instances of the same problem. Example, a function to compute the factorial of a number or to traverse a tree structure. Base case or stopping condition. The condition that terminates the recursion. It's the simplest form of the problem, where the function does not make any more recursive calls. Without a base case, recursion would continue indefinitely, leading to a stack overflow error. Example, in the factorial function, the base case is when n equals 1. Recursive case. The part of the function that reduces the problem and calls the function again with a smaller or simpler input. This step moves the recursion toward the base case. Example, in the factorial function, the recursive case is when n is greater than 1 and the function calls itself with n-1. Stack or call stack. The call stack is a data structure that keeps track of function calls in most programming languages. Each time a function is called, a new stack frame is created on the stack to store information about the call. Recursive function calls push new stack frames onto the call stack. Once the base case is reached, the stack begins to unwind as the function returns its results. Example, each recursive call to the factorial function adds a new stack frame, which is eventually removed once the function completes. Tail recursion. A form of recursion where the recursive call is the last operation in the function. In tail recursion, the result of the recursive call is immediately returned, which allows for optimization, or tail call optimization, by the compiler or interpreter to avoid adding extra frames to the call stack. Head recursion. A form of recursion where the recursive call is the first operation in the function before any other computation. This means that the recursive call is made before any other operation happens, and the function will not return until all recursive calls have been made. Depth of recursion. The number of recursive calls on the call stack at any given time. The depth increases as the recursive calls are made and decreases as the recursive calls return. In the case of a deep recursion without an adequate base case, the call stack may overflow, causing a runtime error. Recursion tree. A diagram that represents the recursive calls made by a function. Each node of the tree represents a recursive call, and the branches represent the recursive calls made within that function call. The recursion tree helps visualize how the problem is broken down and how many times each function is called. Conclusion. Recursion is a powerful tool, but it's essential to ensure there's always a clear base case to prevent infinite recursion. While it provides a clear and intuitive way to solve many problems, it must be used with care, ensuring that the function has a proper base case and that recursion is well structured to avoid inefficiencies. When used correctly, recursion can lead to clean, maintainable, and elegant solutions to complex problems. Thanks for watching the video.